we're going to talk about more properties of singularities. So let's start with this. So this is called Riemann's theorem of removable singularities. Suppose F is hollow on omega except for a singularity. Singularity is always going to be sing dot from now on at z0, and F is bounded in the punctured ball BR prime around Z0 for some R. So it doesn't matter how small R is, but we have a singularity here where we can put a tiny ball around it, and in that punctured ball, the function is bounded. Okay? Then the singularity is removable. Which means that we can just give it some particular value. We can define f of z0 to be something, and then that thing will be a nicely holomorphic function. There will be no more singularity there. Yeah? Okay, proof. So this is a local result, right? So we are taking some open set, where there's some singularity, and all we need to do is to define f on this value z0 so that it's holomorphic throughout this region, including z0, right? So we can just restrict everything down to just a ball, which makes no loss of generality. Yeah? So this is our picture over here. Let's blow it up. So this is the ball where we have our one singularity here at z0. And we've taken our radius so that we know the function is actually going to be bounded inside this radius. And inside the punctured ball around this radius. And let's take the following contour. Let's pick some z inside this ball, like this, some arbitrary z, and let's take a contour that does this, that goes around the ball. Should need a red so you can see it better. Goes around the ball like this, and let's go up here, go around the singularity, go back, and then keep going around like this. Yeah? And let's let the size of this this is obviously a keyhole contour, let's let this size of this little ball here be size delta. So this is size delta. Okay? So let's call this contour gamma of delta. And then notice the following. So we pick z inside the ball, the punctured ball. Obviously we don't want z to be z0 yet. And define contour as shown. Obviously, it depends on the thickness of this little hallway here, but as you know, we're going to take this down to 0 very quickly, so we don't care about that. So let this be as shown. Then let us apply Cauchy integral formula. Yeah, because this is a nice simple closed curve, right? So by Cauchy integral formula, what do we have? We have that f of z equals 1 over 2 pi I, integral around this thing, gamma of delta, of f of zeta, zeta minus z, d zeta. Just Cauchy's integral formula, simple closed curve. There's no problem anywhere in this, right? If we can, on the interior of this closed curve and on its boundary, it's analytic, so you can apply Cauchy integral formula and we're all good. Yeah? And then we're going to let the size of the hallway go down to 0. Okay, now I feel guilty about not giving a parameter for the hole. So let alpha be the width of this hallway here. So we can let alpha goes to 0, and as we've seen lots of times, because we're going with orientation going around like this, so going down this way, and then we go around, and we go up this way, and as we let alpha goes to 0, these two straight paths cancel each other out, and they just vanish. Yeah? They just vanish. So this gives us that f of z is equal to, what do we have? We have the anti-clockwise integration around the outer ball, which is good, right? So we have 1 over 2 pi I, the integral around the boundary of the outer ball around z0 of f of zeta over zeta minus z, d zeta, minus, now we have what happens when we do the inner ball. If we do the inner ball, we are going clockwise around it. We're going clockwise around it, and therefore we're going to have a minus, right? We're going to have a minus the integral around the inner ball, because by default, this thing is oriented anti-clockwise, right? Cool. All right, so what I'm going to do is I'm going to let this thing here just go down to 0. Sorry, let this delta go down to 0, which means that this entire thing will go down to 0. So let's look at this term. Let's put it in a box. So if we take the absolute value of the thing inside the box, then it's going to be less than the length of the curve, right, which is just going to be 2 pi delta, times the supremum of the stuff that's in the inside. Yeah? Yeah? So it's less than 2 pi delta times the supremum over this boundary of this ball of radius delta around z0 of f of zeta over zeta minus z. Well, obviously supremum with respect to zeta, right? All right, tell me why, as we let delta go down to 0, this entire thing goes down to 0. Everything you said was good. Keep going with that. So where are we integrating around? We're integrating around this little ball here. Yeah? We're on the boundary of the ball, yeah. F is bounded, yeah, yeah. F is indeed bounded, yeah. It's bounded by, yeah, delta's going down to 0. So for every point zeta here, yeah, we are happy about the f of zeta because this is uniformly bounded, because f is uniformly bounded on this punctured ball of radius r by whatever constant, we don't care. No? What about this thing here? You said it's non-zero. Is that all we need? We need to have a lower bound. Indeed. We want the minimum to be non-zero. We need to have a lower bound. Yeah? Good. Very good. Indeed. No matter what zeta we have, the minimum distance between z and zeta is always at least this thing, yeah, which is some non-zero distance. Yeah. So the supremum is bounded by the supremum of the f on the top divided by the infimum of the denominator on the bottom. Yeah? Because to make this as big as possible, we want the numerator to be as big as possible and the denominator to be as small as possible. Yeah? So then this thing is less than the supremum, zeta belonging to the boundary of the ball, z0, f of zeta, over the infimum of zeta belonging to the boundary of the ball, of this thing. Yeah? Cool. And both of these things are bounded universally for every zeta around this little ball for some constant that depends on the z and depends on the bound on the f in this neighborhood, but it doesn't depend on the zeta. Yeah? Oh, I forgot to put this 2 pi here. Yeah? Give me a thumbs up if you're with me here. Okay, cool. So then this is less than 2 pi delta c for some constant c. Yeah? So if I start putting labels and saying what this distance is, and then giving a label for the supremum of f on the punctured ball, then it looks messy, but I'm hoping you guys are all with me with this, that there is a constant c like this, depending on z, depending on the constant of the bound on f on the punctured ball, and but this constant exists, and it's independent of zeta, so we just have this bound. Yeah? Yeah? And it's also independent of delta, right? As we let delta go smaller and smaller, then this thing is only going to get bigger and bigger. Yeah? And this thing remains the same. Yeah, give me a thumbs up if you're with me. Cool, okay. So constant c independent of delta. Brackets. But it definitely does depend. Oops, depending on z. I don't want to write anymore. Depending on z and on the supremum of f on the punctured ball. Okay, so limit as delta goes to 0 of the stuff in the red triangle, red rectangle is indeed 0. Cool. All right, so what that means is that since this delta is arbitrary, we can let it go down to 0. That means we've established that for any z, inside this ball, we actually have that this formula is true. Any z inside the ball not equal to the singularity. Yeah, that's what we've shown. Cool. All right. So keep this in mind as I erase the board and tell me why we can prove this theorem, why we can give f of z0 a value and everything will be fine and we'll have a holomorphic function. What was our situation? We have the singularity at z0. Yeah? We've taken some ball of radius r, and we've shown that for any z inside the punctured ball, we have that f of z equals 1 over 2 pi I, the integral around the boundary of this ball around z0, and then f of zeta over zeta minus z dz. Yeah? And our claim is that we can remove the singularity, we can just give f of z0 a value, and we're all good. Why is that true? All we need to do is to just find some complex number such that f of z0 is this complex number and everything will be fine, we'll have a holomorphic function, what would be a natural candidate for this value of f of z0? I can just tell you, but it's way better that you come up with it. So look what we've got, look what we've established. Let's try that. So define f of z0 to be equal to this 1 over 2 pi I integral around the boundary of the ball z0 f of zeta over zeta minus z0. This is indeed something meaningful, right? We have f is defined at the boundary of the ball. This is a meaningful quantity, so we can indeed define it this way, right? Why is this good? How do we know we don't have a discontinuity here? How do we know we haven't just stuck some value way off where everything else is? Why did you suggest this, Laura? Okay, let's just think about this function. So think about the function z goes to 1 over 2 pi I, the integral around the boundary of the ball, around z0, f of zeta over zeta minus z0. I should have said f of zeta minus z. Think about this function. Is this a nice function? Do you believe this thing is continuous? If we shift z a little bit, is this gonna be continuous? What do you think? If we shift z a little bit, then what happens? Then this thing on the bottom shifts a little bit, yeah? Yeah, and z is something inside the ball, yeah? So are we gonna have continuity? Yeah, so long as we're not on the boundary of the ball, then we're gonna be fine, right? Yeah? All right, so it seems to be continuous, this thing, yeah? All right, let's get ambitious. Maybe it's better than continuous. Could it be differentiable? If we take some z inside the ball and we try and take the derivative, will that work? I mean, we could just check it out, right? We could just take a look. So let's just call this something so that I have some notation. Call this f tilde of z. And if we do, f of z plus h minus f of z over h. Z is inside the ball. We're going to take h sufficiently small so that z plus h is also inside the ball, right? And what's this? This is 1 over 2 pi I, the integral around the boundary of the ball, z0, f of zeta. And let's actually put zeta to the side because we're going to get a complicated expression. So we're going to have f of zeta. And then we're going to have 1 over zeta, z plus h, minus 1 of zeta minus z, like this. Oops, this should be a h here. Yeah? So let's put the 1 over h here. Like this. Yeah? And we're not taking a limit yet, so I can just put the h through, right? So I can just put the h through. And then this becomes this. Yeah? All right. So look at this thing. What's going to happen to the expression in the box as we let h go down to 0? What is this thing as we let h go down to 0? What is this thing? Come on. We are looking at a, don't tell me explicitly what it is, just, it's a derivative, right? It's a derivative. It's a derivative of what function? Yeah, this is just the definition of derivative, yeah, for the function 1 over zeta minus z. And it's 1 over zeta minus z differentiable function. Where is zeta? Where does it live? Yeah. So once we look at this expression, right, so we're not thinking about zeta for the time being, we're just looking at this expression, and this is a perfectly nice function to differentiate, yeah, for any z which is inside the ball. Yeah? So this limit will exist, it's just the derivative. So this thing is a sequence of functions parameterized by h. Yeah? Yeah? And if this thing tends uniformly to its limit, which is just the derivative of this function, then by what we've learned, we can pass through the integral and we'll actually have a derivative. Yeah? So this thing is a differentiable function. We can just differentiate it. It is minus 1 over zeta minus z to the 2, and then we have another minus, so it just becomes this. Right? So in the limit as h goes to 0, this thing goes to this function. Yeah? And indeed, for any fixed z inside the ball, this guy will go to this thing uniformly. For every zeta around the boundary of the ball. This is stuff we did before. This is stuff we did before when we differentiated through the expression of Cauchy integral formula. This is, again, one of these methods. This is one of the key methods we do. We have something which we can write as an integral that allows us to do nice things like differentiate through the integral and get nice expressions. This is another basic method. Yeah? And as you said, when we have something that we can represent as an integral, it is nice. It is nice. We have nice things that come out from it because of exactly this trick. If it's not coming back, then you need to go back and read over what we've done. Read over the Cauchy integral formula, read over the proof of Cauchy integral formula for derivatives. It's just as from this method, right? Cool. All right, are you happy now? Yeah? Now this thing is a differentiable function for any z inside the ball. Yeah? Cool. All right, excellent. So what does that mean? That means that we have this function f tilde. By what we've established, f tilde is equal to f for anything inside the punctured ball. So therefore, we can simply extend in this way, because now we have a function that completely agrees with f, and we have a value at the center, z0, which when we let f0 be this thing, we have a holomorphic function. The singularity no longer is there. We can forget all about it. Do you see what I mean? Yeah? So let me summarize this. So thus, f tilde is holomorphic. Then f equals f tilde on the punctured ball, and so defining f of z0 by star removes the singularity. And its removal singularity. This is the result established. This is the result established. Yeah? Cool. So once again, what's the statement? The statement is that if we have an isolated singularity, yeah, where in some punctured ball around it, the function's bounded. It doesn't matter what constant is bounded by. It could be bounded by 100 million. Yeah? Then actually it's a removable singularity. It's not a real singularity. Yeah? Not a real singularity. Cool. Cool. All right. This is useful because it allows us to characterize singularities. Yeah, let's just do a corollary first, so corollary. If f has an isolated singularity at z0, then the limit as z goes to z0 of f of z equals infinity is equivalent to the z0 as a pole. Okay, proof. So one way is trivial because we've defined a pole to be when 1 over f turns out to have a 0, right? So if f has a pole at z0, then 1 over f has a 0. At z0, right? Now we've done this lots of times, but let's just write it out. So we have f of z is equal to z minus z0 to some m and then some holomorphic function g, like this, yeah, where g of z0 is not equal to 0, and therefore this thing is equal to 1 over z minus z0 to the m g of z. Yeah? And as we approach z0, 1 over g of z approaches 1 over g of z0, which is just a complex number, and we are blowing up. Yeah? We are blowing up. Yeah? So the limit as z goes to z0, f of z equals infinity. And we've talked about this before. Yeah? Now it's the other way we want to think about. So I'm going to erase the board. In the meantime, you think about the other way. Suppose we have that the absolute value of f of z tends to infinity as z goes to z0. Tell me why that means we have a pole in this sense, that 1 over f is a 0. Okay, so the other way. So suppose the limit as z goes to z0, f of z equals infinity. Why does that imply we have a pole? 1 over f of z. What do we know about this function? In particular, that has the consequence that if we're in a small ball around z0, what about this function here? It's bounded, right? So there exists such that r bigger than 0 oops. One over f of z is bounded. In the punctured ball around z0, yeah? So it's bounded in the punctured ball, yeah? So we can extend it so that it's actually a holomorphic function defined at z0, which will have a 0 itself, yeah? So 1 over f of z. So whenever there's a removable singularity now, I'm not going to give the new function we define when we remove the singularity a different name. I'm just going to keep talking about the same function. because it's just going to multiply notation, and once we know the singularity is removable, we can just pretend it's not there. Yeah? So 1 over z is actually holomorphic in, I feel wrong about saying that, so see, so we can think of 1 over z as being holomorphic. After extending in this case, it's trivial what we extend it by. We extend it by 0. But the key point is that 1 over f of z is holomorphic. To the entire ball. And you might think, okay, this is kind of trivial because we definitely know that the thing to extend 1 over f of z by is 0 because f of z is blowing up, yeah? Which is true. But again, the key point is that now this is a holomorphic function on extend by 0 because of this argument that we had. Yeah? Cool. So the function is hollow in b over 0. And we have to have that it has a 0. So actually, let's give itself a different name. The function h of z h of z equals 1 over f of z. And h of z, 0, is equal to 0. Yeah? So, that is exactly the definition of having a pole. We have a holomorphic function with a 0, such that 1 over f of z is this holomorphic function with a 0. Yeah? This is exactly the definition. Of a pole. Yeah? Cool. So, that is the proof of this. And now we can do the classification of singularities. So, classification. One. If f of z is bounded in the punctured ball for any r bigger than 0, then removable. Actually, this is an if and only if. So f of z is bounded in the punctured ball is equivalent to z0 is removable. Because if it is removable, then for sure that's true. Yeah? For sure that's true. Because once we remove the singularity, then we have something holomorphic. So in a small ball, for sure it's bounded, so that's definitely true. So that is the first kind of singularity. The second kind is that if the limit as z goes to z0 of the absolute value of z0 equals infinity, this is equivalent to f has a pole. That's at 0. And then what's left, if neither of these things true, I guess it's I before E. Then it's the only other thing it can be, it's an essential singularity. And if we think about the example of the essential singularity we thought about, it was this, right? Yeah. So it definitely wasn't the case that this thing remains bounded as z goes to 0. We saw that, right? But it's also not the case that this thing blows up to infinity. If we approach 0 along the complex numbers, then this thing just went spiraling round and round 0. Yeah? Remember this? Yeah. So we have three kinds of singularities. We have the singularities that essentially are not there, where in some neighborhood around the point it remains a bounded function, and then nothing's actually happening there. It's a false singularity, it's a removable singularity. It's something like z squared minus 1 over z plus 1, right? This thing is removable. Removable singularity at z equals 1, minus 1. Right? A priori, this thing isn't defined at minus 1. Yeah? But just some algebra, we know that this thing is equal to z plus 1, z minus 1 over z plus 1, yeah? So then this thing actually is just equal to z minus 1, yeah? And at this minus 1, we therefore just need to define this to be equal to this thing, which is minus 2, and we've removed the singularity, yeah? So there's no real singularity here, it's just the way somehow our function came out. And we basically don't have to worry about this kind of singularity. Yeah? Or we have a pole where it's doing something pretty uniform. It's blowing up towards infinity, and it's blowing up towards infinity in a very understandable way. Yeah? Whatever the order of the pole is, it's blowing up like absolute value of z to the n, if n is the order of the pole. Yeah? Yeah? Or we have these crazy guys that don't do either of these things. They behave in an insane way. They don't actually blow up or remain bounded. They do some combination of the two. So this is the prototypical example. This is the prototypical example. Yeah? Cool. All right, so let's prove a theorem about essential singularities. This theorem comes with a name. It is Weierstrass. Casorati, something like this. Weierstrass. I don't know how to spell this. All right, so I'm probably misspelling these names, but these are Weierstrass, of course, you've heard of. All right, so suppose F has an essential singularity at Z0, then for any r bigger than 0, the image of the punctured ball around Z0 closure is the entire complex plane. Yeah, it's the entire complex plane. Okay, so that says that if we take any little ball around our singularity, then this thing is completely covering the entire complex plane. Yeah? So it's wildly expanding and covering up the space. There's actually a stronger theorem by Picard that every single point in the plane, complex plane, is hit twice, except for, not twice, it's hit infinitely many times except for one point. So it is wrapping around the complex plane infinitely many times except for one point which it misses and only hits once. Not once, but it doesn't hit infinitely many times. Yeah? So this is dramatically bad behavior. Yeah. I mean, if you remember your multivariable calculus, the image of a ball, its error is something we can calculate, right, with this change of variables formula, right? So typically we could integrate around the Jacobian in the domain to get the error of the image. Yeah? But since the error of the image is infinite, that means that the Jacobian of this thing is infinite. It's incredibly expanding, or the integral of the Jacobian is infinite. It's incredibly expanding space. Yeah? So this is dramatically singular behavior, so proof. Suppose this is false. So there exists some, zeta belonging to the complex numbers, take away the closure of this thing. Yeah? That means that there's some specific distance between zeta and anything from the complex ball, because this is the closure, right? So this is an open set, so we can put a little ball around zeta. Yeah? So for some we have actually that there's a ball around zeta which is inside the complex plane, take away the closure of this thing, again, just because this entire thing is an open set. Yeah? So, consider the function say h of z, which is equal to 1 over zeta minus f of z for zeta inside this punctured ball. So, tell me cool things about this function h. It doesn't blow up, right? Why not? It's more than never equal to z. There's some distance, right? So the gap between, or the distance between zeta and f of z for any z in this punctured ball is at least delta. That's what we know, yeah? So the absolute value is less than 1 over delta by construction, because this thing is always bigger than delta. Yeah? So tell me other cool stuff about our function h now. What about h at z0? What is z0 for h? Is h defined at z0 when I just do this? Given our hypothesis, if I just ask you what h of z0 is, can you give me an answer? F has a singularity at z0, so we can't give f of z0 a value, right? So h is defined out of f, so a priori we can't say, we don't have a value of h of z0 yet. Yeah? So that is exactly what we mean by singularity. It's something where it's not defined yet. But we've got this property. So, tell me cool things about h then. What kind of singularity does h have at z0? Start again. Does it have a pole at z0? So we've learned about singularities. We've learned there are 3 kinds. Let's list them off. Huh? What would happen if we have a pole? What would you expect from h if it had a pole at z0? Yeah, if it had a pole, then this thing would blow up as z goes to z0. That's what we just learned, huh? So does it have a pole at z0? Yep. Yeah. So it can't possibly have a pole because it's bounded. In fact, this property being bounded as we approach z0 is exactly necessary and sufficient to be a removable singularity. Yeah? So h has a removable singularity. At z0, and that gives us this bountiful extra good stuff that we can think of h as just being holomorphic. So think of h as holomorphic. In the actual ball, not the punctured ball. Okay, cool. But then if h is holomorphic, we can change things around. Let's wrap this around. We have this is equal to 1 over h of z, which implies that f of z is equal to 1 over h of z plus zeta, like this. Yeah? Cool. All right, so now, what is going to happen as z goes to z0? This zeta is just a constant, right? So we don't have to think too much about that, right? So when z approaches z0, what happens to f is really depending on what happens to this thing. Yeah? Okay, so what are the possibilities for h at z0? Could h of z0 just be some number? Is that possible? Some non-zero number. Why not? Yeah, no, if this thing was just some non-zero number, then as z goes to z0, then f of z just goes to 1 over h of z0 plus this zeta, which is just some number, so it tends to this limit, it's not blowing up, yeah? No. Okay, so could h of z then have could h of z0 therefore be 0? Okay. Jaime, you're doing lots of good stuff, answering many questions. Can someone else explain why no? Why can we not have h of z0 being 0? Okay, and why is it the case that we know that it's going to infinity? H is what? No, it's not to do with continuity. So, oh, I take that back. Actually, continuity is enough. Continuity is enough. Yeah. Yeah. So since it's continuous, as we let z get closer and closer to z0, then h is getting smaller and smaller, so this is uniformly blowing up. Yeah? Cool. Cool. So continuity is enough. I was about to tell you the fact that we know the zero is of the form z minus z0 to some power is what we are using, but we don't need that actually because we've proved this result that blowing up to infinity is equivalent to having a pole. Yeah, so it's enough that it's continuity. Good. So this limit would be equal to infinity. So a pole. So neither of these things are possible because by hypothesis we have an essential singularity. Therefore, what does that mean? That means there does not exist any zeta which is inside the complex numbers take away the closure of the image of the ball. Yeah? So this is indeed a crazily badly behaved function as we approach z0. This is wild behavior. And this is showing that this behavior that we looked in some detail of this function e to the 1 over z is somewhat generic. If we kept playing with that function, we'd see that it really does have that property. It's wrapping around the entire complex plane just in any small neighborhood of 0. And that's what any essential singularity does. So when we have a bad singularity, then it's really bad. And if we don't have a bad singularity, then we have actually really rather good singularities, rather manageable singularities, either removable singularities, which we can just forget about, or poles, which are extremely regular and controllable in the way that they are singular.